You're ready.
Okay, thank you. Thanks for the invitation. And also, I'm Jimmy Huang from the FinAI. It's a great honor to be here today to present our recent progress from the community, the FinAI, towards AI readiness in specific domains for medical, finance, and legal. But today we are going to just talk about our recent progress for the large model applications in finance, including 4 important topics we discovered during our prior experience for the past 2 or 3 years: the benchmarks, models, agents, and applications. Although today's topic is mainly about the finance, but I believe there are many common bottlenecks, challenges, and solutions that can be shared between those specific domains like medical and legal. So hopefully you can get some insights from my show today. Before I jump into today's topic, I want to give you a brief introduction of the FinAI, including its initiative, community, and collaborators. The FinAI is actually an open research collaboration community towards AI readiness in specific domains, including its focus including open science, open applications, and open infrastructures. So this research community was set up February last year. So we observed that there is a huge gap between the research of large language models and its applications for real-world applications for those specific domains like medical, finance, and legal. Apparently, finance is our first area that we jump in with those large models and to discover what we need to do to fill this gap. And then we also explore other areas like legal and medical during our collaborations, including collaboration with the BISC here. And AI readiness is actually a term proposed by our collaborator, the Linux Foundation. It is a term describe the maturity of AI techniques before it can be really applied to the real-world applications. So as you can see, like the whole community is trying to foster the open source research in this area so we can fill this gap. And finally, we can adapt these large models for the real important tasks in those specific domains. Nowadays, we have focused on 4 different aspects, as I also included in my talk title today. And we now have over 20 research groups from our top university and institutes around the world, including Yale, Columbia, University of Florida, and the other top university from both China, UK, Japan, and the other areas of the world. And they are organized into different working groups. We have a specific working group for different topics related to every aspect we are interested in, and we think that can, push forward the studies in the specific domain. Except for that, we also have outside collaborations. We are now the associate member of the FinNotes Foundation, which is the financial branch of the Linux Foundation, focusing on the open source financial software. We are currently in collaboration with them in exploration of large models for many open source financial softwares. We are also the official collaborator of NVIDC, which is the NVIDIA Research Center, and they will kind of support us for all our computing resources for upcoming 2 or 3 years. We also have a long-term collaboration with Hugging Face, focusing on both datasets, benchmarks, models, and leaderboards. And besides that, we're also in connection with many research centers, including Archimedes in the EU, the Craft Center, which is the first center in US that are sponsored by NSF, focusing on the FinTech, and also the Necton in UK. So just to give you a brief review of our community here, today I will give a talk covering our explorations for the past 2 or 3 years, applying larger models in financial area, including the 4 topics I mentioned again and again in today. First the benchmark, then the model, followed by the agent, and finally is the federated learning. As you can see, it covers the life cycle of the larger model when you try to apply with a specific area or specific issue. So today we will review all the work we have done for the past 2 or 3 years around these 4 topics. So first of all, when people try to apply large model with specific domains such as finance, legal, and medical, the first ever question we raise is like, how do existing large models perform on the task and the scenarios of the specific domain? Especially, those existing large models for example, ChatGPT or GPT-4, they are not designed or even trained on the specific domain. So the question people will arise is like, could we directly apply these models with my task or scenarios in this specific domain? How would they perform? This leads to our first community project here, focusing on the financial benchmarking for larger models. This is a community project that consists of, as you can see, a lot of research groups and institutes under our community. And FinBen is our latest research outcome, which is accepted by NIPS dataset and benchmark last year. So we have a serious work under this project, including PISHO, which is the first financial benchmark for larger models, which is also set by NIPS 2023. And our latest work, which is a user-centric financial benchmark, is accepted by NACO, just reviewed 2 days ago. Yeah. So in the following, I will first quickly introduce the background, the method and contribution for this work, so you can get a brief idea of what we have done with the benchmarking here. So first of all, we both know that the advanced large model exhibit remarkable capabilities, not only on general domain, but there are a lot of research, even some of them are conducted by our community, showcase that they have these abilities on financial text analysis and prediction tasks. However, the large model itself is the whole area is quickly advancing itself around all the directions. Just in last week, we just witnessed the 3 important models, maybe the most important models in this year, the DeepSeek V3, the DeepSeek R3, and the other models. I believe Kimi just released their latest models. So we need the financial evaluation benchmark to tell everyone what is happening today, what exactly those new models, what potential bottlenecks and issues they address with the new techniques today, and what remains to be the challenges for these models. That's why for the existing models, actually, there are a lot of general domain benchmarks like MMU, Helm, Big Bench. Those benchmarks you can find in every model's technical report. And you can directly see from their report like how they performed. For financial benchmarks, there are also some like the Flu, BBTC, and also PISHO. PISHO is our prior work, as I mentioned earlier. So although there are a lot of benchmarks, they are still limited. First of all, for all these existing financial benchmarks, they only focus on the financial OMP task. And I think this is also common for also the medical and legal area, right? The first benchmark or the following benchmarks or the majority of benchmarks nowadays for this person, everyone just to reach the low-hanging fruits, just to create a lot of NLP tasks for those large models in specific domain. But for finance, and also I believe this is also common for legal and medical, is when actually for practitioners, for stakeholders, for regulators in this area, they require the performance evaluation for those real-world applications and issues. For example, for finance, they do want to access the performance of those large models for forecasting, for risk management, for report generation, and also for decision-making. Therefore, that's why we propose the first comprehensive financial large model benchmark here. It first includes 42 data sets spanning around 24 financial tasks. As I mentioned, this is a huge effort. That's why we need a community to do that. We organize them into 8 categories. The first 4 categories are just the traditional financial NLP task, including information extraction, textual analysis, question answering, and text generation. And then we include another 3 important categories we extract from the needs from those practitioners, including risk management, forecasting, and decision-making. And finally, we have a category, the Spanish, focusing on the multilingual ability for those large models in financial area. The first highlight of our work here is that we apparently, compared with existing work, we introduce significantly larger number of tasks and data sets. And secondly, we are the first benchmark ever that includes the evaluation of stock trading into the financial large model benchmark. To do so, we implement both the agent-based evaluation and the reg-based evaluation, which we will cover later. And we also propose 2 NOAA open source data sets. The first data set for regulation compliance in financial area, and the first data set for stock trading to support the stock trading, as I've just mentioned. And finally, based on this benchmark, we also want to foster the research based on the benchmark. We want to call more people to jump in this area. And we now have the benchmark here. We notice that the large models underperforms on those financial tasks. And for computer science, apparently all those specific domains like medical, finance, and legal, they're kind of like the rising areas, not those old areas that everyone have a lot of experience. So we just want more researchers from the computer science community to jump into this area and push for the study for these bottlenecks we have observed with our benchmarks. So we also hosted the financial large model first show task focused on hosted on last year, the FinOP workshop at the EJCAI 2024. And following that, we'll have 3 new show tasks hosted at the workshop on coding this year, just closed 2 days ago. It attracts much attention from both academia and industry, both attracting, I think, more than 40 teams to join this to join this challenge and share their solutions with us. Now let's delve into the details of FinBen. So firstly, for all the categories, I want to briefly review some of the categories. For information extraction, just like the general domain, we focus on the NER and the research extraction. For text analysis, we include the content and sentiment analysis. For question answering, we evaluate their ability to comprehend and respond to financial text. And for text generation, we just assess the generation ability for those large models. These are common settings for general domain, also for financial domain, and for other domain like medical and legal. Besides that, there are 3 categories that focus on the specific applications in the financial domain. For risk management, we ask the model to evaluate. We evaluate the model for their credit. We ask them to detect the fraud and ensuring regulatory compliance. For forecasting, we ask the model to forecast the financial future trends. And for decision making, as I just mentioned, for the first time, we access model ability in sequential decision making for the financial decisions. And lastly, we also evaluate the model's multilingual ability with the low resource language Spanish. Apparently, the resource in Spanish is much sparse compared with the English. To do so, we just collect all the data sets from 3 major data sources. Firstly, we have collected all the open source data sets from existing computer science and financial studies. We just designed the diverse prompts by domain experts and reformulated them into instructions. We also collect the data sets from our existing works and the other existing financial evaluation benchmarks like PSHO and FLES. And finally, we propose our 2 novel data sets here. For FinTrade to support the trading, we just include not only the stock prices, but also the news, company filings for 10 stocks over a 1-year period. And for regulations, we are the first ever to curate a data set focused on the long-form question answering related to the OTC derivatives and financial regulations within the EU section. Based on these data sets, we proposed the 42 tasks. Apparently, a lot of them are just inherited from existing studies and our existing books. So for information extraction, we include the NER version extraction, but also some tasks from specific design for financial area, like the numerical labeling and textual analogy. For textual analysis, we include sentiment analysis and news headline classification. For question answering, we have those. The question answering is totally different from the general domain. We have this question answering that requires the model to extract information from both textual and tabular inputs and ask the model to perform the mathematical reasoning based on that. And we also have the text generation task and the forecasting task focused on stock movement prediction. For risk management, we just cover all the 4 major categories we just reviewed earlier. And lastly, for trading, this is what we will cover later, is we build the first agent-based trading evaluation. We build an agentic framework which empowers the large model to perform the trading in simulated markets. And finally, for Spanish, we cover all the important data sets and compare its performance with English. For the benchmark, we evaluate 21 representative general large model and financial large models, including ChatGPT and also Llama family. For financial large model, we cover those large models fine-tuned for the financial area, and also those models continue to train for financial area like Xuanyuan. All the evaluations are performed on 16 A100 80 GB GPU with over 600 GPU hours. It's very high cost. If you want to perform it again with a market price A100 GPU, it will cost around $51,000. So thanks God we have NVIDIA to cover it all for us. Finally, what do we get from the benchmark? This is the results for the whole benchmark. This is I'm sorry, because the results are too large, so I do not find a better way to visualize it. So what can we learn from it? For information extraction and textual analysis results, GPT-4 stands the best. But we do observe that for fine-tuned model like FinMA, they show a better performance even compared with GPT-4 on their fine-tuned task, which proves again the efficiency of fine-tuning for the specific task once you got the data. But however, it struggles with the task that it never include in its training corpus, like the IE tasks. For question answering and text generation, again, GPT-4 and Gemini are the best performed models. And we see that larger models show better performance in those generation tasks. But for forecasting and risk management results, remember, this is the first ever introduced into the financial evaluation for those large models. For these real world scenarios, all large models fail to meet expected outcomes and lag behind those traditional methods. And this become even worse for large models with low instruction following ability. We do observe that for risk management, those type data sets, they have a very high balance of data sets. So for example, for fraud detection, only 2% of the data are fraud and the other users are normal. But those large models will directly classify all users into not fraud, which is not a fantastic answer. Also, additionally, for Spanish results, when we compare the performance of those large models in financial area in Spanish compared with their performance in English, we do discover there is a huge language disparity for larger models. For ChatGPT, GPT-4, and Germany, they both show a limited performance compared with their similar task performance in English. And also for open source models, like Mistral 7 billion, they perform competitively, which proves again that you can improve the multilingual ability by adopting those language-specific tasks. And finally, it turns out the smaller models, particularly from the Llama family, they struggle with this domain complexity and the language disparity. Compared with the language disparity we discovered, like previous work reported in the general domain, in the specific domain, the disparity are much more significant. And finally, I want to highlight our decision-making results here. By adopting the agentic framework for the first time ever, we can adopt a large model for sequential decision-making problem in finance, which is trading. And therefore, we can evaluate them as a trading strategy using all the economic and financial metrics for those trading portfolios. As you can see, GPT-4 shows a superior trading performance with a larger than 1 Sharpe ratio. And all large models show better performance than buy and hold. This reveals the potential for large models just acting as a decision-making, the core of a decision-making problem. But however, only large language models larger than 70 billion can generate trading actions, while those smaller models like 730 billion fail to do so. We suspect this is maybe they are hard to, smaller models, they are difficult to handle multiple input sources and also the complex instructions required for the trading task. Also, based on this benchmark, we further co-hosted this leaderboard. This is co-hosted now by the Finos Foundation and the Hugging Face. You can even find a blog about it. And we don't want the benchmark to be done for once. We regularly update the leaderboard with the latest model results bi-weekly, and they are trying to include more new tasks into the leaderboard. So we want this to be a place where everyone can jump in. If you want to know what exactly happens today, what's the status for the large model in the financial area for their applications, you can look at the leaderboard. And hopefully you can find your task related to one of the tasks here, and you will see what exactly the current performance of those sort of models and what exactly you want in the next steps. Besides that, as I mentioned, we also host the show tasks and challenges in EJK and also in the coding workshop, which closed like 2 days ago. And finally, what we can learn from our benchmarking part here. We believe, from our perspective, the benchmarking is the first step for adoption of large models in specific domains. So if you have any specific needs or scenarios that want to adapt a large model for that, you need to first build your benchmark data set and try to access the performance of existing large models with your benchmark. And also for the whole community or for the whole area, it's important to have a leaderboard. You have a centralized place to let everyone to evaluate the model and show the results, so everyone will know what exactly happened today and what need to do with the next steps. And it's important to keep it growing because there are a lot of models published every day, so you need to update your results with them. However, it is also very time and resource consuming to do so. It's impossible without support of a community. We are lucky that we are supported with not only our community, but also the Finos Foundation and also the Hugging Face and even NVIDIA to push forward this project. And finally, what do we learn from the benchmark results here? What do we learn from the current status results of all large models? We do observe that current large models, although they show extremely well performance on the general domain tasks, they still struggle with the fundamental task in specific domain. This indicates there is a huge knowledge gap for those general domain large models to be applied with these specific domains. So based on that, the next question would be, how could we enrich the domain knowledge of existing large models? Since we already observed that they are kind of incapable of doing domain-specific applications due to this gap. So based on that, we also have a community project, Open-FinLLMs, which is open multimodal large models for financial applications. Again, this is a joint effort from almost all the groups from our community to do so. And the computing resources are supported by the NVIDIA Research Center. So just also a quick review of why we do that. As you know, currently all the industry are trying to adapt large Gen AI in their real applications. According to the recent report from McKinsey, and the use of Gen AI by industry actually for the financial industry is much slower than the other industries. And based on the recent report from our collaborator FinOps Foundation, they just interviewed the practitioners in the financial service industry. The lack of in-house skills and domain knowledge for those large models are in the top 5 reasons for these practitioners not adopting Gen AI into their daily workflow. So, and also this is equal to what we have observed with our benchmarking work. This is aggregate statistic from our FinBen benchmark. And as you can see, the overall average scores for even the SOTA model GPT-4 on 8 categories of FinBen is less than 40 score on a 0 to 100 scale. Apparently, this is not enough for specific domain when you try to choose a large model for your specific needs. Then the question is how to improve large model in financial application. There are 3 ways to do that currently. The first method is to pre-train from scratch. The advantage is very obvious, right? You can fully enhance large models once you got a very large scale of domain corpus. But the disadvantage is like it's slow, it's high cost, and hard to follow up with the general domain. You need to do it again and again. And each time you need to do with a full pre-training from scratch. And in contrast, the instruction tuning seems like a better way to do that. It's fast, it's cheap, and you can even adapt it with the downstream domain specific tasks. And you can empower the large model with instruction following ability. However, it also has a bottleneck with knowledge. Apparently, only a small portion of the parameters of those large models are updated with a limited domain datasets. It also requires a huge human annotation efforts, especially when you try to apply a large model with an area that no one have done any NLP-related task before. You need to manually annotate all the datasets for yourself. Compared with them, the continuous training, the third way is currently maybe the most optimal way to do that. And you need to do that with the continuous training. It's cost efficient, and you can integrate the whole models with the up-to-date domain data. Existing work actually in financial area, there are a lot of attempts previously to try to enrich the large models with the financial knowledge. The Bloomberg GPT is the pioneer work in this area that pre-training a new model from scratch using all the data they have in Bloomberg. Following that, there are also a few attempts last year, like Fincher, to continually train the larger models with domain-specific corpus in finance. And apparently, there are also a lot of work focusing on fine-tuning the large models using the financial instruction data, like Fisher and FinGPT. Even we have done this before. But the challenges, there are 2 major challenges for those prior work. Firstly, they still utilize a very limited domain-specific corpora, which we will cover later. And secondly, except for Fincher, all those prior attempts are focusing on the text modality and they ignore the other modality. For example, charts and tabular that are very important for financial analysis. But except for Fincher, even Fincher itself only focus on the charts tabular and ignore the tabular modality during the training and inference. And finally, they have very limited evaluation scenario. Apparently, before FinBen, they even cannot find a benchmark to do that. So they only evaluate the few short and instruction fine-tuned scenarios for those models, which is not enough for people to fully access the performance of those large models. So just so, we propose Open-FinLLM, which is a series of financial large models tailored for complex financial applications. This is a fully open source. Also, this is in contrast with what Bloomberg GPT and also Fincher, they do not release the models until now. So our first effort here is FinLLama, which is a fundamental model, continually trained over 52 domain tokens, which is the most comprehensive financial corpus for continuous training up to now. Based on that, we further instruction fine-tuned our foundation model, utilize over 500,000 financial instructions to empower it with the downstream task adaptability and also the instruction following ability. We also further extend our models with the multimodality using over 1 million multimodal image text instruction pairs, including charts and tabulars. And finally, we comprehensively evaluate all our models with all the scenarios we think that users in the end may need. For example, like the zero-shot, few-shot, and also the trading scenario for our foundation model, the instruction fine-tuned evaluation for our instruction model, and also the multimodal evaluation for our multimodal extension. Let's get into the details of these models. So first of all, for our foundation model, we first mix our domain corpus with the general data. This is very important. And the ratio here is we just is the best ratio we get from our mix-up experiments. And this is very important because there is an important issue for contributor training, which is so-called the catastrophe forgetting, which means that during the contributor training, the model itself will lose the knowledge it gained from the initial pre-training from scratch. So you need to mix your contributor training corpus with the original training corpus during the pre-training from scratch to avoid it from forgetting everything you learned from the learning from scratch. It's kind of very tricky to do that, but you need to find the optimal ratio to mix up those data to avoid this issue. And inside our financial corpus, we have the most comprehensive financial data, including the financial papers, conference calls, financial reports, technical indicators, news and social media, historical data, and SEC filing. As I mentioned, this is the first time ever to include not only the textual data, but also the tabular and time series data that are very important for financial models to analyze those, to be applied into the financial area. And as you can see from the left table, many of these data types are the first time ever introduced into the contributor training corpus of financial models. Our back model was just based on the Llama 3 8 billion. Based on that, we further fine-tuning our model, instruction tuning our model with the domain task instruction tuning dataset. We also have the most comprehensive financial instruction data. As you can see from the tabular, we have not only the financial instruction here, but also some a large scale of mathematical reasoning instructions pairs from here, because we observe that mathematical reasoning is very important for financial area application. I want to include the instructions from this domain. Except for that, finally, we also extend our model with multimodal abilities here. We choose the clip as our visual encoder and design a 2-layer MLP for the projector. It consists of the two steps for the multimodal extension. Firstly, for pre-training, we just fix the textual LLM decoder and also the image decoder and utilize over like 600,000 instruction textual image pairs to tuning the multimodal projector itself only. And after this phase, we further fine-tuning both the projector and our large language models using over 800,000 financial instruction image text pairs for further fine-tuning. Our back model just choose our own foundation model. Finally, we access performance of our models and compare it with like the SOTA models in different scenarios. First of all, for our foundation model, we compare our models with Llama 3, our backbone model, Bloomberg GPT, the pioneer model in this area, and also Llama 3.1. So we do not choose Llama 3.1 just because several days before we release our models, Llama 3.1 released. So we have to compare with. It's always a pity to do so. And as you can see, luckily for Llama 3.1, it only shows a better performance on several mathematical reason-related tasks. And for the other task, it doesn't show a great performance. This is kind of like in contrast with its performance comparison in the general domain, which tells us like all the new general models, they do not always show a better performance in the specific domains. So for our models, compared with all these back models, we show a great improvement by incorporating those financial specific texts into our contributor training corpus, which indicates again the importance for continuous training on the specific domain. And we also compare our model with Bloomberg GPT, but unfortunately, it do not release the model until now. And as you can see, even compare with the pre-training from scratch, our model shows a better performance. This is because the Bloomberg GPT is a model from 2 years ago. So our model is a fine-tune from the latest Llama 3 model, which means, as I mentioned, Pre-training from scratch using all the corpus of domain corpus data may not be an optimal choice, because sometimes the general domain does have a much higher performance than you. Then you need to adapt your model with it. We also evaluate our training performance again using the same agentic framework we introduced in the FinBen. As you can see here, we have imposed the large models with all the possible modules we think to have for the sequential decision making. For the inputs, we include not only the price data, but also the news data, the 10K, 10Q, the company finance data. And finally, we ask the model to perform a single asset trading task. We conduct our experiments on 4 important assets here. As you can see, compare with the other backbone model, like the Llama 3, Llama 3.1, our model shows a much better performance in trading, which potentially indicates that we have a better financial knowledge for this sequential decision task in financial area. Except for that, we also evaluate FinLlama instruct, compare with all the SOTA models, like ChatGPT, GPT-4, and also the SOTA financial model like Fincher, Paramia, and also the open source SOTA model at that time, Mr. 7 billion. As you can see, our model even outperformed GPT-4, 3 out of 6 data categories. Even for the other 3 categories, we show competitive performance, and our models is the best over all open source models. I must highlight that this is not a fair comparison, because our model has only 8 billion parameters, and ChatGPT or GPT-4 may have like hundreds of billions of parameters. Finally, we evaluate the multimodal performance of our multimodal extension. We compare it on 4 datasets here. 2 datasets are from the MMU, which is commonly used multimodal datasets, and also is section in business. But these datasets only focus on the financial images. We also propose our 2 new datasets here, focus on both charts and tabulars, and we compare our models with those SOTA multimodal large model like GPT-4 Germany, Tianwen series, and DeepSeek series. As shown in the results here, as you can see, although we are the best in 1 of 4 datasets, but actually in that tabular bench, we are outperform all other basins, including GPT-4. And for the other 3 datasets, we are still the best over all open source models, although we are kind of like still have a gap between the GPT-4. But for financial area, actually, the financial images are not that important, but the tabular and the charts are more important than financial images. That's why we have these 2 new proposed datasets. Models do perform better on these datasets. This is a case study to indicate what exactly we do with the tabular and charts. This is very common because we extract these questions from the daily practice of those fund managers and analysts. As you can see, we ask the model not only to extract the information from those charts and tabulars, we do ask them to perform a basic analysis, including some basic mathematical reasoning over those extracting information. And finally, I want to give a discussion on the use of our open-FinLLM large models. And I think this is also common for the other areas like medical and legal. For foundation models, it's better if you got more annotated data for your task, and you can fine-tune the foundation models in the specific domain for your usage. And in general, it will show better performance than you directly fine-tune those general domain models. For instruction models, this is more suitable when you have no knowledge or no prior data sets for your task. You can directly apply those domain instruction fine-tuned models, and in general, will show a better performance than directly apply those traditional BERT models. And for multimodal models, it's simple. Once your inputs incorporates not only the text modality, you should use this model for your task. We also have limitations for this task. First of all, although we want our model to be fully open, but we do realize the Llama models actually have very strict community protocols. It's not fully open. The Llama 3 models actually is become strict, much more strict, and it is get banned in the European area. And also the information for this foundation model can be out of date. That's why you need to do the contributed training or even fine-tuning again and again with all the up-to-date informations. And also these models, although it show a better performance on sequential decision-making scenarios, they still have limited sequential decision-making ability, because large models, as I mentioned, for contributed training, for fine-tuning, they are trained for next token prediction. These are text generation tasks, not the sequential decision-making tasks. And finally, although our model has only 8 billion parameters, according to our feedback from our industry collaborators, they are still complaining about the deployment of those models, because for 8 billion parameters, it still requires like 60 gigabytes memory of the GPUs, which also sometimes it requires some advanced GPUs, because you need to require on some abilities of those advanced, the most up-to-date GPUs libraries. And finally, what we learn from our practice for doing this model project. First of all, from our perspective, continuous training and fine-tuning still is the up-to-date optimal way to enhance large model in specific domain. And if you want to find your solutions for the specific domain, the better way is like you find some continuous trained foundation models, you collect some annotated data, then fine-tuning your model with that. And somehow for continuous training, it is still extremely high cost, which means for this continuous training project, we cost like around $500,000 if you want to replicate the efforts. So, and also it still need to follow up with the general domain solutions. After this project, we immediately start the next round for our continuous training, because we need to catch up with the latest progress in the general domain. So based on that, once we got the benchmark, we know the model is not enough, and we now have a better model with enriched knowledge of domain. Is that enough? Not. As I mentioned in the limitations, those models are not trained for the decision-making programs. They are trained for next token prediction. That's why in the past year, we witnessed that most common applications for large models are chatbot, right? Because they are designed for that, they are trained for that, and you can only apply with that. So the problem is like, for specific domain like finance, like medical, like legal areas, the most important and fundamental tasks are sequential decision-making tasks, right? For finance, it means trading. For medical, it means diagnosis. For legal, it means judgment. A lot of tasks are related to this fundamental problem. So how the new question arises is, how can we apply large models in sequential decision-making problems in specific domain? To answer this question, we propose a synthesized LLM multi-agent system with conceptual verbal reinforcement for enhanced financial decision-making. This is also accepted by NIPS last year. So to do so, we just give everyone a brief introduction in case you are not familiar with the LLM agents. LLM agents, as I just introduced, LLM itself, although it showed great performance in those text generation analysis tasks, is still not enough for making high-quality sequential decisions. This is proved again and again by a lot of prior works. So therefore, researchers, especially researchers from the cognitive science area, they have successfully proposed LLM-based agent. That's why you heard agent a lot of times last year and this year, designed to try to overcome this limitation. As shown in the bottom image here, the agent itself is a large model, but we enrich it with 3 important components here. First is the tools component. We just added the large model with the ability to calculate, to interpret the code, and to search around a given corpus or database. Based on that, we also have the memory component, which should allow the model to have both the short-term and long-term memory. Besides that, the most important thing is we empower the model with the planning component. A lot of the material design here, you are quite familiar in the past year, including the reflection, self-critique, transfers, and sub-goal decomposition. As you can see here, we just simulate the decision-making progress of a human. All the components are borrowed from the cognitive progress of a human. And we just empower the large model with all the essential components that we think are very fundamental for human to make a decision in the real-life scenarios. However, existing large model-based agent frameworks, they are still not enough, lack of the sufficiency and flexibility to support the complex reasoning and the decision-making scenarios in special domain, like finance, like medical, and legal. That's we just present the 4 important gaps in the tabular in the bottom. The first 2 gaps we show here is domain-specific for finance, because we realize that for maybe you will also realize those bottlenecks and limitations for different domains like medical. For finance, those agent framework, they lack the risk control because you need to control risk apparently during the trading. And also they are unable to do the portfolio management, which is a term described like you are not a trade on only one single stock, but you try to balance your money among several assets, several stocks. Except for that, the last two gaps we think are common for all specific domains. So first of all, for a single agent, if you try to apply a single agent with a specific domain applications, it will show an undermined decision quality due to the comprehension and reasoning pressure very heavy for a single agent. That's why what we propose here is multi-agent system. We want each agent to focus on a single task or single role. So by collaborating, organizing them together, we will have a better system that can handle such complex decision problem. But it also will bring not only the advantage, but also the extensive pure communication cost. And also the optimization goal will be unclear for multi-agent system. That's why we designed the synthesized manager analyst hierarchical communication structure. This is specific design for the financial area. As you can see, it simulates what exactly a human organization like a hedge fund or investment bank, what they will do to perform a financial trading decision, which we will introduce the details later. Then let's come to the details of our methodology. We first model these two decision-making tasks as partial observable Markov decision process. This is a term from the reinforcement learning, which means we can model this as a decision-making under the framework of reinforcement learning. Then we propose the optimization problem via a conceptual verbal reinforcement learning method. Based on that, our framework, as shown in the diagram. First of all, the first highlight here, we want to effectively extract all the signals from all the inputs. This is also common for medical. We want to collect all the information that a human utilizes for their decision making. That's why we cover the multimodal market environmental information in the first block. In the second block, we want to integrate our framework simulate with a broad range of large models. Actually, we want all large models can be plugged in and to utilize our model for the decision making. And the third block here is all the functions modules we mentioned previously. We empower the large models with the external tool to enhance their abilities for single agents. And finally, in the last block, we operate all the agents as a collaborative team, with each agent possessing the human-like or beyond cognitive abilities. And here is the details for the communication structure we designed for the FinCon agents. We follow a hierarchical organization setting, just like a human organization, like a hedge funds or investment banks. In details, as you can see here, in the first layer, we have each individual analyst agent specialized in a specific modality or input resources. And we have after that, we have a single portfolio manager, just as everyone will have a manager here. And finally, we also have a risk management department that ensures that all the decisions are complied with the risk thresholds. So first of all, the analyst agents will take the input with respectively their input resources, like the stock price agent will take input at the stock prices, and they will generate the market insights according to their own abilities. All the market insights will be passed into the manager agent for it to aggregate and to deliver the final decisions. And only the manager agent interact directly with the dual level risk control component. As you can see, finally, we can get it running and let the manager to have the final decisions for our task. Here is the cognitive system of each individual agent. Let's just cover it very quickly. We have all the components that we think is essential for a single agent to empower it with the cognitive abilities for just like a human agent. We have the general configuration and profiling module, and also the presumption module to let it know what exactly the task we're supposed to perform. After that, we also have the memory modules to interact with large models. So large model will have both the short-term and long-term memory, and it will extract essential information according to the task. And finally, the action module is specifically designed for the manager. The manager will be the only agent with this module to deliver the trading actions based on all the insights we generated with the analyst agent. This is the memory module details of our agent. As you can see here, we have both the short-term and long-term memory. For the short-term memory, we designed for each agent. It can interact with this short memory inside each episode, which means a trading period. Inside this trading period, each agent will choose what exactly it wants to put into memory, and we update it, and also extract the selling information from the memory. We also design an episodic long-term memory for the manager, which is utilized for our reinforcement learning. So the manager will update its investor beliefs across episodes from all perspectives. This is based on that, we have the CVRF, the reinforced learning as mentioned, to facilitate manage the agent's belief updates. This is different from the traditional reinforced learning based on gradients. We utilize the reinforced learning to update the prompts for those managed agents. And as you can see here, the last time large model generated those investor beliefs are totally different. This shows that how we can update our reinforced learning. And the reward for this reinforced learning is not from anyone or any human, it's directly from the market signals, right? We receive the feedback from the market once the manager makes the decisions, and we utilize this feedback directly to update the investor beliefs of managers. And it can update the whole investor beliefs across the episode, which means we can train the managers with several trajectories or even millions of trajectories during the simulation, kind of like a warm-up. And after that, we can apply this train managers with our final decisions. As you can see from the right bottom table here, the trading actions from different episodes changes largely. There is a significant distinguishment between the trading action we performed from each episode, which also tells us that our manager learned from our trading. He's learning by doing it, just like a human. So we conduct our experiments on 8 assets, compare our models with like existing large model-based agents like FinGPT, FinMemory, FinAgent, and also deep learning-based method like A2C, PBL, and DQN. As you can see here, our models present a significant better performance. And in some assets, our model is the only method that can outperform buy and hold method, which is the strong baseline from the finance. Actually, this is also aligns with everyone's intuition. Buy and hold means you just buy the asset, hold it for 3 months, and then sell it without any actions. So for any other agents, they even underperform this baseline because it's somehow difficult to make a profit on the markets. But our method, it turns out that we can learn something from the market, and we can apply it with the trading here. We also, our method is also the only multi-agent method that can perform the portfolio management task. We compare our method with the equal weight portfolio. We just equally spread the money into each asset, and also a Markov mean variance portfolio, which is a very classical portfolio management strategy. I think it also has won a Nobel Prize for that. And compared with this classical portfolio management strategy, our method still present a much higher performance compared with them. And finally, we conduct some evaluation study to showcase that our risk control components does attribute to the final performance. First of all, we just compare our method with the implementation of SIVA, which is in the episode risk control component. And it turns out that our method without the SIVA control will show a much lower performance. Except for that, we also compare our methods like the manager without the belief updating with the manager with the belief updating using the CVRF. And as you can see from the result, both single stock and portfolio management task, it turns out that our manager do learn something from the trajectories and also the feedback from the markets. So what we learn from our agentic framework, we believe firstly, the agentic framework is essential for empowering large models with sequential decision-making capabilities. With only the models, you cannot directly apply it with all the fundamental problems in specific domain. It cannot work. Except for that, we also believe the multi-agent structure to reduce the single agent efforts will provide a better solution for those complex decision-making problems for specific domain. Because for trading, for diagnosis, and for the other complex decision-making problems in specific domain, they are too complex. And if you can recall, all the decision-making tasks we included in O1 in the other general domain papers, they just utilize mathematical reasoning or simple logical reasoning tasks rather than the complex reasoning task here. And finally, although I do not present the results here, we also test O1-like in-context reasoning methods in our decision-making task here, and they show limited performance or even underperform previous methods in this task. And it turns out that the O1 in-context reasoning is not a silver bullet for any reasoning task. It requires a better solution for those complex reasoning tasks for those specific domains. Finally, although we got the models, we got the match agent, it seems like we can directly apply large model retrieval applications. But here we encounter another important issue when we discuss it with the industry practitioners, regulators, and the other users. It turns out for specific domain like finance, medical, and legal, the data privacy is a major concern for them to do that. Although they want to apply, they are kind of enthusiasm about the adoption of large models. They are worried about the data leakage for adopting such large model solutions. So our question would be how to deploy large model in comply with the secure, trustworthy, transparency, and privacy regulations in specific domain. To address this question, we also propose HARMONIC, which harnessing large model for tabular data synthesis and privacy protection. This paper is also accepted by NIPS last year. And in this paper, we just focus on the tabular data, which is a common data type for both finance, medical, and legal. And we utilize large models to generate synthetic data and try to protect the privacy and try to answer whether if you can address this data privacy issue with a synthetic data generation. So first of all, I want to briefly introduce what is data synthesis. Basically, you just create a new data set during a generation process based on the original data. And the target is you want to generate new samples related to the original data, but cannot be mapped back to the original data. So it is widely adopted in many areas and nowadays to protect your data. And for previous methods, there are simple augmentation, diffusion-based, and GAN-based methods, but they are nowadays not utilized for LLM-based training because this data ignore the semantic information in the inputs. They can only generate the numeric outputs. And therefore, there are also latest methods trying to adopt large model-based method to generate synthetic data for large language model training. They are great, and we have followed a lot of methods trying to generate those synthetic data for large model training. However, they are effective but risky for data leakage, which we will prove later with our experiments. For evaluation here, there are two categories or two topics to evaluate the quality of the synthetic data. First is effectiveness. We just evaluate whether the generated data is alike with the original data and whether the model trained on this synthetic data can have a performance or better performance on the downstream task. And another topic is privacy. Apparently for synthetic data, we do not want to leak our original data. And for traditional methods, because they are just numerical features in the tabular, they just utilize the distance to measure the similarity between the synthetic data and the original data. So based on that, we have proposed two different methods here. For generation, we propose a synthetic tabular data generation solution, which utilizes the KN to maintain the efficiency and fine-tuning large model for privacy preservation. We further prove that this is equal to a differential privacy generation. For evaluation, we introduced two new metrics to evaluate the effectiveness of privacy of synthetic data in the era of large models, because previously all these metrics are designed for machine learning methods. And now we introduce two new metrics that are designed for large models. If we can apply this synthetic data with the large model training. And for generation, the first step is very simple. We just construct the instruction data set using KN to find the similar rows. And we then find instruction tuning the tabular data synthesizer to generate, the objective of it is to maximize probability of generating the correct output samples given the similar original samples, and also to protect the privacy. Based on that, we can sample all the synthetic data using our synthetic data generator. For evaluation, we first propose the large model evaluation efficiency metric, which we just fine-tune the large model using our synthetic data and apply it with the real test data set to see if it has a better performance. And for data leakage test, this is specifically designed for large models. We comparing the difference of the perplexity between a generator or a real data and the synthetic data. So a higher DLT values indicates that the generator is more inclined to generate the data that are much similar to the original data. It has a leakage potential that the generated synthetic data could still leak your original data. So we conduct our experiments with 4 classification data sets spanning around different areas, including finance, medical, and legal. We compare our method with the baseline those synthetic data generator, and we evaluate using all the metrics here. We adopt the Llama 272 billion chat as a base model, and we also perform some ablation studies here. As the experiments show here, firstly is the effectiveness. It turns out that our method can show a comparative performance to existing sort of approaches in those synthetic data generator. And by saying so is that we still underperform those classical data sets for the metrics related to machine learning methods. But for large language model related metrics, we show that the model trained on our synthetic data can show a better performance. For privacy data, as everyone concerned, is like our models can protect the privacy. The generated synthetic data can have no variations compared with the original data. But however, it also indicates that the large model synthetic data generator, the previous generator, pose a significant risk of data leakage. It's high possibility. They will generate the synthetic data that everyone can utilize it to get back to your original data. And nowadays, everyone is using like the synthetic data for their data set generation or large model training. So this is a huge potential risk that needs to bring to everyone's attention to do that. Our take-home conclusion for this is very simple. Nowadays, for large models, weights are the data. So everything we tried in the era of machine learning changes. For value learning, previously we just think past the weights with the differential privacy is safe. And now even the synthetic data generation using large model still need to consider privacy preservation. Otherwise, you will still, in case, you will lose your original data by doing so. Finally, I want to give a brief, kind of like our views from the community, combining all our suggestions from our working groups for different components for the next few steps. For benchmark, we consider like for all the special domains, more languages and more modalities are the future directions. Because nowadays people want to adopt large models, not only in English-speaking countries, but for other countries. So it requires you to have the multilingual benchmark to access performance of large models. That's why we also have the ongoing project focusing on the Greek financial large model leaderboard. And it turns out like there is no previous effort to do that. Except for that, for the benchmark, it also requires people to craft the benchmark, more focus on the real world cases based on some agentic framework. So everyone will know exactly what this large model can perform with those scenarios, instead of the simple natural language processing tasks. And finally, a very critical bottleneck for benchmarks, like for nowadays for specific domains, everyone has the data, has their needs, but they do not like to review their data to the model part. So although they want to know how large model can perform in their own private data, they do not want to show it. So the proof of abilities without showing the data model will be a critical step in the future. Like how can we prove the ability of large model to a private data side without even utilizing their own data? This is called the zero knowledge proof. I believe this will become one of the popular topic in the upcoming 2 or 3 years. For the model part, we do observe that for DeepSeek and the other models, at least in this year, mixture of experts with smaller models will become very popular. This is due to the training limitations of those large models. They are too expensive and it requires too much data to train. So everyone we are focused on training, continually training smaller models for not only specific domains, but for lower scale at each specific topic or skills. Such as a code large model or math large model, and just composing those smaller models with mixture of experts. And as I mentioned, those models are still lack of the abilities for decision making. This cannot be achieved by next token prediction. So reinforced learning augmented with those large models will be the next, I think will be the next direction for model training. For the agent part, for the specific domain, apparently, instead of a fixed structure agent that can only be adapted with a single scenario here, auto planning with dynamic collaboration of those agents are very important for the agent architecture design in the specific domain. Except for that, also how to co-evolve those multi-agents with the multi-agent reinforcement learning algorithm, so the whole system can learn from the whole environment. Again, just like a single agent, we need the multi-agent to co-evolve with the environment. We need to learn from its failure, from its success. That will also be the next topic. No one have done this before. And finally, for the deployment, as I mentioned, it's important nowadays we try to aggregate all the private data from the specific domain. Course different size, but the traditional family learning is not working anymore. We cannot directly pass the weights. Nowadays, for the large model, weights are the data. So how to implement a course size privacy preserved family learning is very important. We do observe several private works in this area trying to adapt the traditional fat learning with large model in contributed training and fine tuning, but they do not focus on the privacy preserving because they are general domain. It's okay for them to just utilize data. But for specific domain like finance and medical legal, this could be a huge issue because everyone need to comply with the HIPAA, right? That's all for my presentation today. Thank you for your attention and time. Please stay tuned with our community and feel free to join us. You can see our URL here. You see our URL from the site here and our leaderboard. Thank you. And I'm open to any questions you may have.
So I'm more interested in real world scenario. So I know many people, they buy NASDAQ, right? So I believe NASDAQ have a lot of talented people reading public news, insider news, financial reports, or like stock trade for like top 500 companies. But somehow those people come to a decision, the top 10 holdings as like Apple, Google, or some other company. So I'm wondering, in the future, can we make a financial large language model to do that and beat NASDAQ, like in the long term, past 1 year, 12 years, or 10 years? And then maybe it's a way to commercialize it. So people don't buy NASDAQ, it will buy your product, make more money in the past, like in the long term.
Yeah, that's a really good question. Actually, after our multi-agent work published in the NIPS, even at the NIPS, a lot of people ask us, have you just invested like thousands of dollars in your algorithm? Does it work at all? Can we just invest in your strategy? What I can tell you is like, for now, is an initial point for us to do that. And we just simulate the progress you described, aggregate all the input resources, empower the large model so it can have the ability to trade and also learn from the trading. And to do so, there is still several issues that before we can turn our offline back testing into online trading. The first thing is the latency, because large model is, the inference speed of large model is much slower. And the second, apparently it is very crucial, and every trading companies, West banks live by that. So there's a lot of work to do that before moving from the simulation to real world trading. Yeah.
The point is, when can we give you the money so you can?
Maybe in this year you can buy our portfolio. You know, in the end, we are trying to do that.
So you see the news, the Trump had the coin, what's that? The Trump memo from
German
if you bought that one, it's like how many times? It's like increased over 24 hours, like 60 times or something like that.
Yeah. Cryptocurrency is also another topic. We are currently in collaboration with a few like the traders and also trading platform in cryptocurrency. But it's still in progress. Stay tuned. Maybe someday we can open the floor.
No.
Okay.
One is that I want to know what are the management and then focus in developing specific development. Does that mean that if we have a massive amount of data, then we can adapt the existing release model to do the question of so how to update the existing models? Do you say you update your coverage to vacuum
Okay, thanks. These are very great questions. So first question for the training of those specific domain models. The major bottleneck here is the mixed up ratio for different data sets. Actually, you will notice that for your task or for your model, you will aggregate different types of data, and you need to determine the ratio in the continuous training or fine-tuning data sets. This is currently, they are just empirical practicing. Everyone just try it and find the optimal ways there. I think this is one of the topics they try to explore in top computer science community conferences. And to do so, you need to try it again and again. I believe for DeepSeek and for the other companies, they do it. They may learn something from the mix-up ratio experiment, but we never know. If you want to train your own models, you need to try it with your own data set and find the optimal mix-up ratio based on that. And for this also related to the second question you have, how could we update our model with the latest data? As I mentioned, there is a recent paper I remember publishing last year, NIPS or ICLEAR. They just showed us that if you want to continuously train a model on a fine-tuned or previous continuously trained model, it doesn't work. Again, the catastrophe forgetting. The models will forget what it will learn during the continuous training if you want to adopt it again with the continuous training. So if you want to update your model with the latest data, the current optimal way to do that is you just mix up your data set again with the original data set and try to find a new mix-up ratio. That's maybe the possible way to do that. I don't know if there are any new techniques or tricks to address these two issues, but they are basically the major bottlenecks here. And apparently it costs a lot of money to do that. Every time you try it, it means you continue to train a model. It costs like $500,000 to do that. Thank you.
One idea I suggested to make that cheaper is to use KL divergence of the probability of the existing corpus rather than inserting the trained examples.
Yeah, that's also a very good suggestion. Actually, there are a lot of work focusing using the perplexity, the KL divergence, and the other measurements to handle the balance of data sets. But it turns out even inside each continuous training data set, the quality diverse. And which means, the quality for each data inside each data set, you may have different contribution to your continuous training corpus. Some of them may help with some tasks and some of them may be not beneficial for the other tasks. So it's difficult to tell, you can use some distribution measurement to handle this. And what we observe so far, we utilize like the Doremi and the other, methods that consider this as a bilinear optimization problem based on the distribution similarity matrix for balancing those data sets. It doesn't work. For all the tasks, we will observe that there is only one optimal ways, and also it depends on your downstream tasks. So just try it again. The ways we derived from those distribution similarity measurements and also the optimization method, it doesn't work at all. Yeah, that's our practice here. Thank you. Okay.
I don't really have like a super deep finance background, so I was hoping you could like just go a little more into detail.
Yeah.
Like in stock trading, what a prompt looks like, what the output looks like, and like what the input, just like what the input and output for like a single instance of stock trading.
Yeah, that's very simple. Just imagine what we try to simulate here is this agent is just as a human. Imagine you are a human. You want to perform stock trading. What do we read? We read previous price features, right? Just as the lines and curves, right? For those price features, the open price, the close price, right? You also read news about these stocks, and you read their company finance, which is their annual reports of their management status. You just read them. Or maybe someone tell you, like your aunts or your relatives tell you, just buy it, right? So these are the analyst reports, the news, the company finance, the stock prices. These are composed as the inputs for those agents. And the outputs is very simple. We just design very simple trading tasks for those agents, because if it is more complex, then it cannot work. So the simple trading is like we just ask the model to generate the 3 actions for one single stock: buy, sell, and hold. It either buy it with all its money, or sell it just with all the positions, or just hold it with the previous status. So the input output could be like this.
And the benchmark is just like peers. They're just like in your benchmark data set that used to evaluate against like, all these other models plus like buy and hold or whatever.
Yeah. So once we empower the large model to have the ability to generate these three actions, we can actually get is the profit and loss, right? Versus the trajectory of its actions. And then we can compare each model, right? Each model can generate its own actions and it will get its own profit and losses with the market. And the buy and hold is very simple with no actions. We just buy it at the first, hold it for 30 days or for the whole trading period and sell it. It's very strong based on actually a lot of strategies people think that are very active or effectively that cannot beat this baseline. Okay. So for our model, agent framework, we show that with this agent framework, you can trade and sometimes it beats the buy and hold baseline.
So if you like say high frequency, like the models people would use it like high frequency trading.
For high frequency trading, this is a totally different story because for the low frequency trading, like the intraday trading, you have more time to read all the resources and traders at the same frequency, they read the same resources just like you. And for high frequency trading, we are talking about not seconds trading, we are talking about milliseconds trading. They do not have time to read so many resources and all the information resources doesn't change between the trading period. So all they need to read is the order book. It's kind of like the book recording all the previous buy and sell prices for the same asset, and they need to make the decision in milliseconds. To the best of my knowledge, and know that they do have several companies apply large models with high frequency trading, but this that is a total different story. Yeah.
And like you have a lot of like our LLM versus other LLMs, but like not a lot of just like versus machine learning.
Oh, we also compare our method with those deep learning based methods, and it turns out our method still outperforms them. Yeah, but maybe this is I don't know, it could maybe a coincidence, right, for the financial markets. But we do compare with the traditional reinforcement learning methods. They utilize the 3-layer or 4-layer neural networks as their policy network. And it turns out our method shows a better performance compared with. Okay, thank you.
One more. Yeah, sorry. Yeah. Yeah.
Okay.
So since the Shubha said, and so since there is latency in the language model and the benchmark is offline, so you have multiple benchmarks like QA or something to test the performance of these financial models. Have you considered online benchmark? Like, yeah, you provide APIs and this algorithm are tested to trade, to like hold, like buy or sell, and maybe like 1,000 money and then put $1,000 in each algorithms, and you give it like one month to test whether this algorithm is well success in the trading. Maybe yes, because all the benchmarks currently like picture or other benchmarks that's offline. But in like that sense, there's some like online benchmarks.
Yeah.
So have you considered to try online platforms to offering the online benchmark to test these algorithms so in the real scenarios?
Yeah, that's a very interesting suggestion. Actually, we are actually in the progress doing that. Yeah, we are in collaboration with some trading platform discussing if we can have a live trading benchmarks, right? We can directly apply our large models to each day trading. Maybe not using the real money, but in a simulated trading platform to do so. But as I mentioned, from the offline scenario to online scenario, it requires a lot of efforts, not only for the algorithm part, but also for the development part. You need to get into their environments, get connected with their data APIs to gather the data, and also get connected with their trading APIs to perform the trading actions. And also, as I mentioned, the latency of large models will be very important here. Although we can do it daily, but imagine that you have a benchmark and you want to benchmark at least 10 models, right? It requires a lot of time and also compute resources to do that. So we are still in the progress exploring this. But as I mentioned, this is a very interesting idea and we are currently exploring it. Yeah. Thank you. Okay, thank you again for the invitation.